Aristotle conjectured that objects fell towards the Earth because of Earth being the center of the universe and all masses were naturally attracted towards it. Galileo established that the gravitational acceleration was independent of the falling mass. After the heliocentric model of Copernicus, Kepler found that planetary orbits were elliptical and quantified how their velocities vary through empirical laws. Newton derived Kepler's laws through a quantitative simplified law of force attraction between masses and his laws of mechanics. Laplace refined Newtonian gravity by introducing the concept of gravitational potential and formulating the Laplace equation. He also attempted to set a finite propagation speed to gravity by considering that the gravitational field was defined as a radiation field or fluid, in which changes in the motion of the attracting body were transmitted via waves. But his model required a propagation speed of gravity over 6 orders of magnitude of that of the speed of light. That was because Laplace assumed that when an object such as the Earth is moving around the Sun, the attraction of the Earth is not towards the instantaneous position of the Sun, but towards where the Sun had been if its position was retarded using the relative velocity. This would cause a pull ahead of the Earth, which would cause the orbit of the Earth to spiral outward, unless the speed of gravity were very high. But Laplace was wrong, since he did not consider the Lorentz invariance of static fields. The attraction towards an object moving at constant speed is towards its instantaneous position with no delay, for both gravity and electric forces. In a field equation consistent with the special relativity, that is a Lorentz invariant equation, the attraction between charges moving at constant relative velocity is always towards the instantaneous position of the charge, in this case the gravitational charge of the Sun, not the time-retarded position of the Sun. This is because the relative motion between the Sun and the Earth is slow and nearly uniform over short timescales, which ensures that there is no observable aberration in the direction of gravitational attraction, even though gravity propagates at the speed of light. After Maxwell, Heaviside formulated gravity using Maxwell's equations in 1893, a theory later referred to as Gravitoelectromagnetism, which is considered the linearized approximation of general relativity. It predicts similar effects of general relativity, such as induced rotation of a falling object, precession of a spinning object, and the Lenz-Thirring precession effect, and the fact that mutual gravitational attraction between two objects will be greater if they spin in opposite directions than in the same direction. But it is not Lorentz invariant, because the mass, energy density, and momentum density do not transform as a 4-vector. They are part of a tensor, which under Lorentz transformations mixes all components, including stresses. In gravitoelectromagnetism, the gravitational field is described by a gravitoelectric field analogous to the electric field and a gravitomagnetic field analogous to the magnetic field. The gravitoelectric field components correspond to the time-space components, and the gravitomagnetic components correspond to the space-space components of the field tensor in gravitoelectromagnetism. Right before Einstein's work on gravity, there was a post-Newtonian period of intense speculation. Many physicists were studying modifications to the Coulomb inverse square law, trying to come up with modified potential models of gravity to include velocity-dependent or retardation effects and explain the anomalous perihelion shift of Mercury with gravity having a finite propagation speed. For instance, in 1870, Holzmüller proposed a law of gravitation of the same form as Weber's electrodynamic law, and later Tisserand used this law to study the anomalous precession of Mercury's perihelion, being able to explain only 14.1 out of the 43 arc seconds per century. Lyman and Maurice Lévy proposed a law of gravitation of the same form as the electrodynamic Riemann's law, where the speed of gravity is equal to the speed of light, explaining 28 out of 43 arc seconds per century. In 1898, Paul Gerber proposed a velocity-dependent potential that accurately predicted the observed value for the anomalous precession of Mercury's perihelion, and he actually derived the exact same formula for the correction of Mercury's orbit as the one from Einstein's General Relativity, although the way he achieved it is a source of debate. Nordström's nonlinear scalar metric theory of gravity can be considered the predecessor of Einstein's General Relativity, and even Einstein stated that only his work with Grossman and Nordström's theory were worthy of consideration in the pursuit of a complete metric theory of gravity. Others such as me and Max Abram were also taking part in the competition. The progress in general relativity by Einstein and Fokker was inspired by Nordström's work, even though no light bending or energy contribution from the electromagnetic field to gravity was present in his theory, and it was not in agreement with observations. The history of progress in gravitation done by quantitative models of gravity that were the most complete at their times can be followed from Newton's law of gravity to heavy-size gravitoelectromagnetism until Einstein's general relativity. Einstein's work is considered nowadays the best description of gravity, and he reached his field equations incredibly quickly after special relativity, in about 10 years. But what if Einstein's great achievement was too ahead of his time? What would the progress in gravity would have looked like if Einstein's theory was developed later? What it could have been done before Einstein is developing the ideas of Ernst Mach with regards to gravity and inertia. Mach hinted that inertia had an origin in gravitation. For Mach's implications not to violate locality, a finite propagation speed must be included, such as that of Weber's or Riemann-based models explained earlier. We explained in our previous videos the ideas of Mach, and in another one how Reissner and Schrödinger independently derive the value of the gravitational constant by considering the kinetic energy term relational and based on a gravitational interaction. Later, Sciama popularized this derivation of the gravitational constant in a non-relativistic vector potential theory of gravity, in which inertia is derived from gravitoelectromagnetic equations, and the inertial law arises as a side effect of gravity, with inertial forces resulting from the gravitational induction of the gravitoelectric field from the whole universe. With a similar model based on the Riemann's potential, such as that of Schroeder's, inertial mass is isotropic, and the weak equivalence principle, an essential principle that general relativity assumes as an axiom, can be naturally explained. All of this could have even been done before special relativity, through Maxwell's equations. Even after Sciama's work, John Archibald Wheeler still considered Mach's principle as a fundamental problem in gravity, as he stated in his report of the 1957 Chapel Hill Conference. This inspired a more Machian modification to general relativity in the Franz-Dicke theory, but as we explained in our previous video, it is not fully Machian, and was abandoned because of requiring a fix to be very similar to general relativity in order to agree with observations. In general relativity, when we observe the motion of a non-inertial reference frame, the motion appears to deviate from geodesics. These deviations arise because the coordinate system used to describe the motion does not align with the geodesic structure of spacetime. The effects of inertial forces in general relativity are geometricized and encoded in the Christoffel symbols, which describe how the coordinates change due to frame non-inertiality, and do not vanish in this case. Thus, general relativity uses fundamentally the same interpretation for inertia as the Newtonian laws. As explained in our previous videos, general relativity does not satisfy all the consequences of Mach's principle that Einstein considered. Would general relativity be the same if the origin of inertia according to Mach's ideas was developed before it? Could Einstein have reached a different version of general relativity if he followed the ideas of Mach, Reissner, and Schrödinger? Apart from the unification of gravity and inertia, and a more fundamental explanation of the gravitational constant and the equivalence principle, other fundamental developments in the understanding of gravity could have been done before and not after general relativity. For instance, 1923's Newton-Cartan theory, which uses the machinery of differential geometry such as a tensor form with curvature, geodesics, and connections to obtain Newtonian gravity, could have been developed even before special relativity and Maxwell's electromagnetism. But it was developed soon after general relativity, which showed Einstein that the use of tensors was not a sufficient condition to achieve a full Machian relativity theory, which was Einstein's failed intention. Even before Carl Schwarzschild came up with the metric solution that was given his name, the components of the Schwarzschild metric could have been derived under the assumption that time dilation in the metric has the same origin as time dilation in special relativity, and taking the speed of the special relativistic time dilation to be the usual Newtonian escape velocity. And even before the curved spacetime formulation of general relativity was developed, Whitehead's quasi-linear theory of gravitation from 1922, which was considered at the time a competing theory with general relativity, could have been developed. In this theory, gravity is not spacetime curvature, but is described by a field superimposed on flat spacetime, with gravitational effects propagating at the speed of light and featuring retarded potentials. The Schwarzschild solution is identical to the one from General Relativity, but Whitehead's theory is linear in the sense that the superposition of two solutions is again a solution, and generally makes different predictions compared to General Relativity when more than two massive bodies are involved. It also made the same predictions as General Relativity regarding the four classical solar system tests: the gravitational redshift, light bending, perihelion shift, and Shapiro time delay. But the debate about the validity of the theory regarding other tests has extended over the previous century. All these theories of gravity were based and tested on planetary and stellar system dynamics. It wasn't until around the 1950s when observations for galaxy rotation curves and cluster dynamics were observed, which did not match the Newtonian predictions which all these theories reduced to in those regimes. After careful analysis, new observational laws, analogous to Kepler's laws, were derived for galaxy rotation curves. This can be summarized as follows. First, tangential velocities in galaxies are generally asymptotically flat. Second, these asymptotic flat velocities are proportional to the fourth root of their visible mass. Third, features in visible mass strongly correlate with features in the velocity profiles. And fourth, Newtonian gravity correctly predicts the dynamics as long as the measured accelerations are above a particular total acceleration scale. And analogous to Newton's work, new modified laws of gravity and inertia were derived straight out of these observations, which became known as modified Newtonian dynamics or MOND. MOND was shown to be derivable from a Lagrangian satisfying conservation laws, but we still lack a phenomenological explanation for it. Curiously, the acceleration scale in MOND matches the gravitational acceleration estimated with the mass and size of the observable universe, and one version of MOND consists in reducing inertia at low accelerations, where field intensities are low due to being far away from other masses. These two coincidences suggest that MOND could have an origin in Mach's principle. We explore these ideas in several videos in our channel. Today, the research for a complete theory which reduces to MOND is currently pursued by many well-known theoretical physicists. But could it be that MOND has an origin in the Machian ideas of inertia that could have been developed before Einstein's general relativity and were developed after due to Einstein's premature development of his theory?